Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh, and very good morning to all students. So today we will continue our discussion on chapter 6. That is discussion on the transmission lines performance. So the contents of the topic for chapter 6 is introduction, and then we have types of power lines that are available, a short line, medium line, and also a long line. So as introduction, this chapter deals with the transmission line model, design and its performance under steady state condition. The equivalent transmission line model is on a per phase basis. So all equivalent transmission will be on a per phase basis. That is voltage line to neutral and also a single phase current. So to model this one, two-port network theory will be used to express the voltage and current relation. And short, medium, and long line model are considered in this topic, as well as the regulation, basically voltage regulation, and also the line losses and efficiency. So if we look at transmission system in Malaysia, so basically we have transmission line in Malaysia is mostly for high voltage AC transmission, and there is a short portion of high voltage DC direct current that is from Gurun, Kedah to Thailand, which is about 110 kilometer long, supply about 300 kilovolt overhead line. And the common transmission voltage in Malaysia are 132 kV, HVAC, 275 kV, and 500 kV HVAC. While in terms of performance of transmission line, okay, the transmission line performance is governed by 4 parameters. So we know that in a electric system, so there must be a series resistance and also inductance, shunt capacitance, and shunt conductance. But due to the shunt conductance is happen due to the leakage current over the surface of the insulator, so we can ignore because the leakage current are normally very small. Okay. And in terms of performance, basically we want to determine efficiency and the voltage regulation here. So the formula for voltage regulation is nothing but voltage at the receiving end under no load condition minus receiving voltage under full load condition divided with receiving voltage at full load condition time 100%. That is for voltage regulation. While for efficiency, the common equation that we use is power at the receiving in 3-phase divided with the power at the sending in 3-phase system. Okay, now let's look at types of power lines. So basically, transmission line can be modeled in three different models. That is short line. Short line, basically, the distance of the transmission line is less than 80 kilometer. While for second one is the medium line, the distance is about 250 kilometer, which means between 80 to 250 kilometer. While for the long line model, usually the distance is more than 250 kilometer. Okay, now we look at the case of short line model. The definition of short line model, as we discussed previously, is less than 80 kilometer in a distance, and the voltage is usually less than 69 kilovolt. So for the short transmission line, usually the capacitance is always been ignored. So we will look at this condition when we see the model. So we can calculate the series impedance per unit length, that is R plus J omega L multiplied by the line length. So if the length is 80 km, so we can get the series impedance from R plus J omega L times the length L. Okay, so this is the equation for the impedance, series impedance. Okay, that is Z equal to R plus J omega L times the distance L equal to R plus Jx. Okay, where R is the per phase resistance per unit length, L is inductance per unit length per phase, L is the line length, and omega is 2 pi f. So depend on the frequency, either 50 or 60 Hz. Okay, shortline model can be represented as in terms of per phase basis. Can be represented as the figure below. So basically, in the common transmission line model, there will be a sending end. Okay, starting of the transmission system is called sending end. Okay, in sending end we has there is a voltage supply here, and voltage supply go through the transmission line. So there will be the sending current. Is the sending current. Vs is the sending voltage. Is the sending current. So the sending current go through to the series impedance Z equal to R plus Jx. Okay, and the output current from the impedance of the transmission line is called a receiving current. IR is the receiving current, and then at the end we have the receiving voltage VR. Also, we put a load, so we will have a apparent power. The power of the load is called receiving power, receiving apparent power at the load. So this part is called the receiving end. Okay, basically receiving is to the consumer or to the industry or to the end user. Sending end is basically the starting of the transmission line. So from this model, we can see that we can make an equation that is Vs. Vs is nothing but the sending voltage equal to Vr. Okay, Vr is nothing but the voltage, receiving voltage, okay, at the receiving part, and also ZIR. Z is the series impedance, IR is the current flow at the receiving part, okay, receiving end. And in this case, Is equal to IR. So if we consider a three-phase load, okay, with apparent power of SR, receiving apparent power three-phase, connected at the end of the transmission line. Okay, SR three-phase is connected here, for example. Then the receiving end current is obtained by this formula. IR equal to S receiving three-phase divided with 3V receiving line to neutral. Okay, so this term means conjugate. So conjugate, what is the meaning of conjugate? Conjugate is just a transformation. For example, S equal to 2 plus J3. So S conjugate will become 2 minus J3. Okay, when we got the value of IR here, okay, so from IR value we can calculate the voltage here, ZIR, and we can add with the receiving voltage, so we got the sending voltage. All right. So for shortline model, and actually basically for all model, it can be represented in terms of two-port network. That is so-called ABCD representation. So you can see from the simplified shortline model, we have the sending voltage, and then we have a sending current IS here. So we have the IR receiving current and VR receiving voltage. So in between that, we can represent as a ABCD or two-port network. Okay. So if we look at the equation, previously we have Vs, that is the voltage supply, equal to voltage at the sending end of supply, same, equal to voltage at the receiving plus impedance times current at the receiving. So this equation we can convert to two-port network ABCD, so we can simplify as this equation. Okay, VR equals to AVR, all right, and ZIR equal to BIR. Okay, so from here we know that A is equal to 1, okay, Z or B equal to Z, okay, while for the case of IS equal to IR, okay, so we can convert this to IS equal to CVR plus DIR, okay, so there is no value for voltage or CVR here in this equation, so C is 0, while DIR, D is equal to 1. Okay, so A is equal to D or equal to 1. Okay, so we convert it in terms of metric form. So Vs, Is or Vs equal to AVR plus BIR, okay, and Is is equal to CVR plus BIR. So we got VSIS equal to 1, Z 01, and VRIR. So 1 is A, okay, Z is B, okay, 1 is A equal to 1, B equal to Z, C equal to 0, and D is equal to 1. Okay, this is the simplified network, two-port network, or ABCD representation for the short line model. So we will use this simplified model. It's the same for the medium and for the long line. Okay, now we look at the voltage regulation in short line model. Previously we have discussed the formula of voltage regulation is defined as the changing in voltage, okay, percent change in voltage at the receiving end, okay, in going from no load to full load. So when there is no load, okay, we call the receiving voltage at no load here, okay, and then minus the receiving voltage at full load divided with receiving voltage at full load here. So we will got the voltage regulation. In simple, we can say that how much voltage change, okay, from no load, okay, then we will give the load, so we will see what is the voltage happen, either increase or reduce, depends on the load condition, divided with the full load voltage at the receiving. It is the formula for voltage regulation. Okay, at no load, for the case of short line, at no load, IR is equal to 0. Okay, there is no load, so there is no current. So when there is no current, IR equal to 0. So from the equation of Vs equal to AVR plus BIR, okay, from this equation, okay, the two-port network, ABCD model. So AVR plus BIR. So when IR is equal to 0, okay, IR is equal to 0. So this part will be cancelled. All right. Remaining equation will be Vs equal to AVR. Okay, Vs equal to AVR. So we can calculate the voltage at the receiving end under no load equal to voltage at the sending, okay, sending voltage divided with A. For short line model, A equal to 1. Okay, previously we discussed that A equal to 1, B is Z, C is 0, D equal to 1. So For A equal to 1, so we have the equation for VR no load, okay, at no load, receiving voltage at no load equal to the voltage supply. Okay, it's clear, of course, voltage supply, and then there is no load, so voltage supply equal to voltage of receiving end under no load condition. All right. Okay, as the voltage at the receiving no load under no load condition is equal to Vs, okay, then voltage regulation can be measured or is a measure of line voltage drop and also the power factor, that is cos theta. Okay, there will be only two conditions. Okay, either voltage regulation is positive or negative. Okay, voltage regulation can be either positive or negative, and also unity. Unity means the voltage at the receiving is equal to voltage at the sending. Okay, so we look at the case of positive, which is lagging power factor. Okay, usually what makes the power factor lag is due to the inductive load. Okay, so we look at the phasor diagram here for the case of inductive or lagging power factor. Okay, positive voltage regulation, which is then the voltage at the receiving end. Okay, this line is voltage as the receiving line under condition of full load. Okay, and then there is a current IR here with the theta. Theta is the power factor cos theta. So IR time R resistance, okay, time series impedance, and 90 degree shifted of JX IR for the inductance. So from this we got Vs as this one. Okay, so in this case we can see that the voltage receiving at full load is less than the supply voltage due to the inductive condition of the load. So the current is lagging by theta degree. So that's why we call the condition is lagging power factor with positive voltage regulation. Okay. Simply we can say we can get the positive by this equation. Okay. Vs is equal to Vr at no load. So this is higher than voltage at full load. So if we minus voltage at no load minus full load, so we will got positive value. For the case of negative, okay, we are negative. We look at this phasor diagram. So VR of full load, we put in the x-axis. So at this condition, the load is more capacitive. More capacitive means that the system is receiving a voltage. Okay, so full load voltage is higher than the sending voltage. So at this condition, if the line current is go to this condition with theta R, with condition of theta, so we will got the power factor of leading power factor. The current lead the voltage. So under this condition, because Vs or VR no load is less than VR full load, so Vs minus VR full load, so we got negative voltage regulation. Okay. Another equation that can be used for sending end power, that is SS three phase. Okay, apparent power at the sending three phase equal to 3 Vs sending voltage time Is, sending current. So this is the conjugate for Is. So just change the signs. If Is is for example 1 plus 2, then it will become 1 minus 2J. All right. And then the total line losses is given by S L, that is line losses three phase, equal to S sending three phase minus S receiving three phase. Okay, So we will get the transmission line efficiency, nothing but power at the receiving three phase divided by power, okay, real power at receiving divided by real power at the sending of three phase. Okay, now we look at the example 6.1. In this example, 60 Hz, okay, short line model is having R equal to 0.62 ohm per phase and L equal to 3.94 millihenry per phase. Supply a three-phase Y connected 100 megawatt load, so the load is 100 megawatt, and 0.9 lagging power factor, so power factor is 0.9 lagging. So lagging means net voltage regulation is positive. At 215 kilowatt line-to-line voltage. Okay. So two questions here. That is calculate the sending end voltage per phase. Sending end voltage per phase. So we want to calculate VS. Okay. And also determine the voltage regulation and also the efficiency. Okay. So this is the transmission line model, same like the previous slide. So we have VS, okay, sending end voltage here. We have sending end current, and then we have the receiving voltage, receiving current, and also the power, receiving power, apparent power, and also this impedance in the transmission line. From the given data, we have R here equal to 0.62 ohm per phase, L 93.94 millihenry. We have also power 100 megawatt, okay, and then we have the power factor. So we can solve this problem or example. So first question is to calculate the sending end voltage per phase. Okay, we want to find the VS. Okay, VS phase. So first we can calculate the series impedance per phase. So Z equal to R plus J omega L. So we use the value given 0.62 plus J 2 pi FL. So we got Z equal to 0.62 plus J 35.41 ohm. Okay, we have the impedance now. Okay, then we can calculate also the receiving end voltage per phase. Okay, given voltage is 215. So to get the receiving end voltage per phase line to neutral, 215 divided with square root of 3, we got 124.13 kilowatt. Okay. From the formula of power at three phase equal to 3 VR line to neutral times IR single phase times cos theta. Okay, IR single phase, this is conjugate cos theta. Okay, so we rearrange this equation, we can get IR single phase. Okay, that is power divided with 3 VRLN cos theta. So given power value is 100 megawatt, okay, divided with 3 VRLN equal to 124.13, okay, VRLN 124.13, okay, kilowatt, and 0.1 is the power factor cos theta. Conjugate, here is conjugate. So we solve this equation, we got the current is 298.37 ampere. Okay. So when we got IR, so we can calculate VS. Okay. That is the sending voltage. It's nothing but V receiving voltage line to neutral plus ZIR. Okay. Just change the ZIR from this value and also Z from this value. Okay. So we got the value for sending voltage is 129.25 kilovolt. All right. Okay, we have solved the first problem. Now, determine voltage regulation and efficiency of the transmission line. Okay. We have voltage at the receiving. Okay. Voltage at the receiving under no load is equal to voltage as at the sending, okay, line to line, equal to square root of 3 Vs line to neutral single phase. So we got set 3 times 1 to 9.25, okay, that is 223.87 kilowatt. So this is voltage regulation, sorry, voltage at the receiving under no load. Okay, so we already have the voltage at receiving full load given 215 kilovolt. So under no load is 223. Okay, 223 minus 215 divided with 215. Okay, so we got the voltage regulation that is 4.13%. Okay. Now look at the power. Okay, the sending power 3 phase equal to 3 sending voltage times sending current. So we just replace all the value and get 100.17 plus J 57.8 mega volt ampere. Okay, so from this value, sending 3 phase is 100.17 mega, and then so yeah, this is equal efficiency equal to receiving power divided with sending power. So receiving power is 100 megawatt. Okay, this is given in the example, divided with the sending power 100.17 times 100%. So we got efficiency is 99.8%. So which is very efficient. Okay, for the case of short line model. Another example of exercise. Okay, you can do a 10 kilometer long or very short. 10 kilometer long short transmission line has 0.5 60 degree ohm per kilometer impedance. Okay, line supply 316.8 kilowatt. Load. Okay, load is 316.8. Power factor 0.8. What is the voltage regulation if the receiving end voltage is 3.3 kilovolt? Okay, so you can make this exercise based on the previous example and try to get the voltage regulation of 16.67%. Okay, you can make it at your own after the class. Now we look at the example 6.2. Okay, in this example, we have 220 kilowatt, 60 hertz, 3-phase line is 40 kilometer long. Resistance per phase is 0.5 ohm per kilometer. Inductance per phase is 1.3263 millihenry per kilometer. So find voltage and power at the sending. So Vs, okay, voltage regulation VR, and also efficiency when the line is applying a 3-phase load of 381 MVA. This is for the case of load 381 MVA, power factor 0.8, lagging 220 kilowatt. Okay, and second 381 MVA, 0.8 power factor, leading at the same 220 kilowatt. Okay, this is the answer for the example 6.2. To solve the question, example, for the example 1, we have example 1. Okay, they want to find the voltage at the sending Vs, voltage regulation, and efficiency. So at example 1, given 381 MVA at the load, okay, 0.8 power factor lagging, and voltage load is 220 kilowatt. So simply we can find the series impedance, that is Z equal to R plus J omega L. Okay, L is the line length, that is 40 kilometer here. Okay, R plus J omega L, L is given by 1.3263 millihenry, R equal to 0.15. Okay, ohm per kilometer. So we got Z equal to R plus J 20 ohm. Okay, then we can calculate the receiving end voltage per phase. Okay, VR line to neutral or VR single phase equal to voltage output 220 kilowatt divided with Z3. So we got single phase receiving voltage is 127 kilowatt. Okay, and the apparent power is nothing but 381 MVA cos 0.1. Okay, so we got the power of 3.4.8 plus J228.6 MVA. So from this power we can calculate receiving current single phase. Okay, power at receiving divided with 3 VR single phase or line to neutral. So we got the current 1000 ampere. So once we got the current, so we can use the current here to calculate the sending end voltage. Okay, we sending line to neutral single phase is equal to we receiving line neutral single phase plus impedance times the receiving current. So we got the sending end voltage is equal to 144.33 kilowatt. Okay, in terms of magnitude, okay, we got VSLL equal to C3 VS line to neutral. Okay, 250 kilowatt. Okay, then the sending end power can be calculated from SS3 phase is equal to 3 VS line to neutral time IS single phase. So we got 322.8 megawatt plus 288.6 mVar or 433 MVA. So we can calculate the voltage regulation. Okay, that is the voltage at no load. Okay, that is this value 250 kilowatt minus 220 watt. 220 kilowatt is voltage at full load divided with 220 voltage at full load. So we got 13.6% and efficiency. Okay, the receiving end efficiency is 304.8 divided with 322.8. Okay, so we got 94.4%, which is slightly less efficiency than the previous exercise example. Okay, for the case number 2, that is the case of power factor leading. Here, okay, you can do by your own after the class. Now we look at the case of median line model. Okay, the definition of medium line model is between 80 kilometer to 250 kilometer length. Okay, for short line less than 80 kilometer, for medium line 80 to 250, and for long line model more than 250 kilometer. In this case, shunt capacitance, okay, shunt capacitance of the line is included and is divided into two equal parts, placed at the sending and the receiving end. Okay, this model is also called nominal pi model. This is like the pi model. So from here we can calculate the total shunt admittance. Okay, that is Y equal to G plus J omega C L. L is the line model. Okay. G is the shunt conductance per unit length, which is usually negligible. And C is line to neutral capacitance per kilometer. Okay. It is more or less same like this the short line model with additional capacitor at the sending end voltage and also at the receiving end part. Okay. So for the case of nominal pi model, so from the equation we can calculate that. Okay, let's look at this model, this equivalent circuit. So we have the voltage supplied at the sending here, and then we have the sending current. Sending current go through the impedance in transmission. So we got the line current, that is IL. And then the output will be receiving current and also the receiving voltage. In between we have the admittance, Y over 2 and Y over 2 due to the additional of capacitance. So we can get the equation here, that is IL, okay, IL is the IL and the transmission line is equal to IR. IR is here plus I and here, that is Y over 2 VR, okay. And then we can get the voltage supply Vs or voltage at the sending end equal to VR voltage at the receiving plus ZIL, okay, impedance of the transmission line times IL, okay. And we can also get IS, okay, IS here, I sending equal to IL, okay, because IL is same like from the initial of the transmission line, is also same like IL plus Y over 2 Vs, okay. Y over 2 Vs is from here, current flow to this part. So we have two different equations, that is for IL plus equal to IR, okay, and this node, okay, IL equal to IR plus Y over 2 VR, and at this node we have a equation of IS equal to IL plus Y over 2 Vs, okay. So we can convert this equation, okay, of IL to this equation, okay. So we got Vs equal to 1 plus Zy over 2, okay, Vr plus Zir, okay. And then further IR, this equation we can convert to this IL, okay. And this also we convert to this one, that is Vs equal to Vr plus Zi, convert to this one. So we got Is equal to Y, 1 plus Zy over 4 Vr plus 1 plus Zy over 2 IR. So we can further simplify, okay, Vr, IR, Vi, IR to the two-port network or ABCD parameter. So we got that A equal to 1 plus Zy over 2, B equal to Z, okay, C equal to Y, 1 plus Zy over 4, this is C, and then D equal to 1 plus Zy over 2, okay, same with A, D is same with A, 1 plus Zy over 2. Representing it to two-port network, so simply like that. So we have discussed previously, A, VR, BIR, C, VR, DIR. So A equal to 1 plus Zy over 2, same like D. Okay, A equal to D, B equal to Z, and C equal to Y, 1 plus Zy over 4. Okay. A and D are dimensionless and equal each other if the line is the same when viewed from either end. Okay, from sending end or from receiving end will be the same. The dimensions of B and C are ohms, and C is mhos. While the determinant of the line metric is unity, that is AD minus BC equal to 1. All right. So we can find voltage at the receiving and current at the receiving if we know Vs and Is. Okay. So from the equation, VR, okay, equal to dVs minus BIS divided with AD minus BC. So we got VR equal to dVs minus BIS. Okay, IR equal to AIS minus CVS divided with AD minus BC. So we can get IR equal to AIS minus CVS. Okay, so in reverse, in metric form or in inverse metric, we can get VRIR equal to D minus B minus CA VS IS. Previously we have VS IS, right? VS IS equal to ABCD here. Okay, A, B, C and D. Okay, and VRIR. Okay. This one, if we look at the sending end, okay, voltage ascending and I current at sending. This one, if we look from the receiving voltage and receiving current, it's nothing but the inverse metric of the sending part of current and voltage. So from here we can calculate voltage regulation, that is Vs, okay, voltage ascending minus voltage at receiving divided voltage at receiving to get the voltage regulation. Okay, look at the example 6.3, okay, 3 to 5 kilovolt, three-phase transmission line, 130 kilometer long. Resistance per phase is 0.036 ohm per kilometer. Inductance per phase 0.8 millihenry per kilometer. Shunt capacitance 0.0112 microfarad per kilometer. Receiving end load 270 MVA with 0.8 power factor lagging at 3 to 5 kilovolt. So we have load 270 MVA and load voltage is 3 to 5 kilovolt. So use medium line model to find the voltage and power at sending end and the voltage regulation. So we can use the same equivalent circuit of medium line model to solve the problem. Okay. The value given is 130 kilometer L. So 0.36, this is resistance R. Inductance here is X. Y we can calculate from the capacitance here. Okay. Okay. Then also the load is 270 MVA here, load 0.8 power factor here also. Okay. And voltage 3 to 5 kilovolt at the load. Okay. So we use the equivalent circuit. Given the value at load is 270 MVA, 3 to 5 kV, 0.8 lagging, and also given the distance of 130 km, R is 0.036 ohm per kilometer, inductance 0.8 millihenry per kilometer, and also capacitor of 0.0112 microfarad per kilometer. So we can calculate the series impedance per phase. Okay, Z equal to R plus JX, so we can calculate this one. So just replace the value of R, okay, L and D given. So we got impedance is 4.68 plus J 39.207 ohm. Okay, to get admittance Y value, we can simply use J omega C times the distance. Okay, here the frequency 60 we use, assume frequency of 60 Hz. So we got J equal to 0.000548899 Siemens. Okay. So from ABCD parameters, so we can calculate A equal to D equal to 1 plus ZY over 2. So just replace the value of Z, okay, of Y. So we got A equal to D equal to 0.98924 plus J001 J0.001284. B equal to Z, so Z equal to 4.68 plus J39.207. C equal to Y, 1 plus ZY over 4. Replace the value of Y, Z, and Y. So we got C is equal to minus 3.5251 times 10 to the power of minus 7 plus J 0.0054595. So now we have the value of A, D, B, and also C value. Okay. So from the given value of receiving voltage line to line, three-phase voltage at receiving is 3 to 5 kilovolt. So we can calculate the single phase receiving voltage, that is 3 to 5 divided with 3, we got 187.64 kilovolt voltage receiving in single phase. So to calculate the receiving current, okay, single phase receiving current, we can divide SR or sending power at receiving power divided with 3 receiving voltage single phase. Okay, so 270 divided with the value of VR, so we got 479.64 ampere. So now we can calculate the voltage and current at sending end. Okay, we have the value of A previously given. We have the value of single phase receiving voltage. We have the value of B, and we have the value of receiving current single phase. So replace the value, we got the voltage of sending voltage equal to 199.19 kilovolt. This is the voltage of the sending voltage. And also we can use the value of C, okay, voltage receiving single phase, D, and also the current receiving single phase. Okay, replace the value. So we got the single phase, sorry, the sending current single phase is equal to 474.42 ampere. Okay, now we can calculate the power at the sending end. It's nothing but, okay, as sending three phase equal to 3 times sending voltage single phase times sending current single phase conjugate. Okay, and we got this value 214.6 megawatt plus J 185.25 watt. Okay, during no load. Okay, during no load, since we can say similar like the previous case for short line model, during no load, IR equal to 0. Okay, so when IR equal to 0, so from the equation of Vs, L equal to AB RL plus BIRL, so IR is 0, so we can simply remove this one. So we got Vs line to line equal to A, VR line to line. So then we got Vs line to line equal to Vs line to neutral times square root of 3. So we got 345 kilowatt. Okay. While the voltage receiving line to line, we got Vs line to line by divided with A. So A is equal to 0.9892. So then we got VR line to line is 348.76 kilowatt. Then we can use the value to find the voltage regulation. Okay. VR no load. Okay. Divided with VR full load. Okay. VR full load is 325. 325. Okay. Divided with VR full load. Okay. This is the value given in the equation 325. So we got 7.31% of voltage regulation.